Hello, imagine a molecule so reactive that it survives for only a few billionths of seconds. Yet, during its incredibly short lifetime, it can destroy antibiotics, pharmaceuticals, pesticides, dyes, and even some of the world's most persistent pollutants. This tiny but powerful species is called as hydroxyl radical, represented as .OH. Hello everyone, welcome to Clean Copper Talks. This is a video series I am preparing on advanced oxidation processes. This is part 2 of the series, and since the most important oxidizing agent in any advanced oxidation process is OH radical, therefore this particular video is about OH radical. After this, I'll make individual videos on each type of advanced oxidation process. So, scientists often call it the detergent of the atmosphere and the engine behind advanced oxidation processes. But what makes this radical so powerful, how it is generated, and why it is considered as one of the most important tools in future wastewater treatment? Let's find out. Hydroxyl radicals are among the most reactive chemical species known to science. They exist only for nanoseconds. For comparison, a nanosecond is 1 billionth of a second. That means hydroxyl radicals disappear almost immediately after they are formed. But during this tiny window of existence, they can initiate extremely rapid oxidation reactions. They attack pollutants that are otherwise resistant to conventional treatment. These pollutants include antibiotics, pharmaceuticals, industrial dyes, pesticides, PFAS, and many other emerging contaminants which are also persistent in nature. Because of their extraordinary reactivity, hydroxyl radicals have become the foundation of more modern advanced oxidation processes. So why do we need hydroxyl radical? Conventional wastewater treatment systems are highly effective for removing biodegradable pollutants. They can effectively eliminate organic matter, suspended solid, pathogens, and nutrients. However, many contaminants present in today's wastewater are designed to be chemically stable or persistent. Antibiotics are manufactured to resist degradation. Pesticides are designed to survive environmental conditions. PFAS chemicals are known as forever chemicals because they are extremely persistent. Similarly, endocrine disrupting compounds and textile dyes can remain in water bodies for extended periods. As a result, these pollutants accumulate in river, lake, groundwater, and aquatic ecosystem. This is where hydroxyl radicals provide a breakthrough solution. Instead of simply transferring pollutants from one medium to another, hydroxyl radicals have the ability to destroy them through oxidation. So why are hydroxyl radicals so powerful? The strength of hydroxyl radicals can be understood through a property known as oxidation potential. Hydroxyl radicals possesses an oxidation potential of approximately 2.8 volts. This places them among the strongest oxidizing agents known. To put this into perspective, chlorine has an oxidation potential of about 1.36 volt, hydrogen peroxide has around 1.78 volts, and ozone has around 2.07 volts. But hydroxyl radicals exceeds all of them with 2.8 volts. Their exceptional performance arises from three important characteristics. First, they are extremely reactive. Second, they are largely non-selective, meaning they attack a broad range of contaminants. And third, they exhibit very fast reaction kinetics. This combination enables them to degrade complex organic molecules rapidly and efficiently. So how are hydroxyl radicals generated? One fascinating aspect of hydroxyl radical is that they cannot be stored. Because they survive for such a short time, they must be generated directly inside the treatment system. Several technologies can produce hydroxyl radicals. Let's look some of the most common methods. UV and hydrogen peroxide. When hydrogen peroxide absorbs UV radiation, it splits into hydroxyl radicals. This process is widely used in advanced drinking water treatment. Fenton process. The Fenton reaction involves ferrous ions reacting with hydrogen peroxide. This reaction produces hydroxyl radicals continuously. It is simple, effective, and relatively economical. Photocatalysis. Photocatalysis such as titanium dioxide absorb Photocatalysts such as titanium dioxide absorb light energy. This creates electron-hole pairs which subsequently generate hydroxyl radicals. Photocatalysis is receiving considerable attention because it can potentially utilize sunlight. Ozonation. Ozone reacts with hydroxide ions in water to produce hydroxyl radicals. This pathway enhances the oxidation efficiency significantly. Sonochemistry. Ultrasonic waves generate microscopic bubbles. These bubbles collapse violently, producing extreme temperatures and pressures. Such conditions facilitate radical generation. Each of these technologies form the backbone of different advanced oxidation processes. So how do hydroxyl radicals destroy pollutants? Hydroxyl radicals remove contaminants through several reaction mechanisms. One mechanism is called as hydrogen abstraction. Here, the radical removes hydrogen atoms from pollutant molecules, destabilizing their chemical structure. Another pathway is electron transfer. Hydroxyl radicals accept electrons from contaminants, initiating oxidation reactions. Third mechanism involves addition reactions. Hydroxyl radicals can directly attach themselves to unsaturated bonds present in many organic compounds. These reactions progressively fragment large pollutant molecules into smaller intermediates. Further, oxidation continues until complete mineralization occurs. Ultimately, contaminants are converted into carbon dioxide, water, and inorganic ions. This is a major advantage. Instead of concentrating pollutants in sludge or transferring them to another phase, hydroxyl radicals can potentially destroy them completely. Applications in India. Hydroxyl radical chemistry is already finding practical applications in India. In Hyderabad's pharmaceutical manufacturing sector, advanced oxidation processes are being investigated to remove antibiotic residues from industrial wastewater. In Tirupur, textile industries are adopting oxidation technologies for effective dye degradation and wastewater reuse. Agricultural runoff containing pesticides can also be treated using radical-based processes. In Gujarat, common effluent treatment plants are exploring advanced treatment techniques to manage recalcitrant industrial pollutants. As India moves towards water reuse, zero liquid discharge system, and stricter discharge regulations, hydroxyl radical technologies are expected to play an increasingly important role. International success stories. Several countries have already demonstrated the successful implementation of hydroxyl radical based technologies. Singapore's world famous New Water project employs ultraviolet radiation and hydrogen peroxide system to produce ultra pure reclaimed water. Japan utilizes ozone based oxidation processes for municipal wastewater reuse. Across Europe, advanced oxidation technologies support compliance with regulations targeting micropollutants. Meanwhile, the United States is investing heavily in emerging PFAS destruction technologies. These global examples highlight the growing significance of hydroxyl radicals in ensuring water security. The future of radical chemistry. Researchers are now moving beyond conventional hydroxyl radical system. One exciting area is selective radical chemistry. Scientists are developing approaches capable of targeting specific pollutants more efficiently. Another promising concept is dual radical systems. Combining hydroxyl radicals with sulfate radicals may significantly enhance degradation performance. Artificial intelligence is also entering in this field. Machine learning tools are helping researchers design better catalysts, predict degradation pathway, and optimize treatment conditions. These innovations could make advanced oxidation processes more sustainable, economical, and energy efficient in future. In conclusion, hydroxide radicals may exist for only nanoseconds, but their impact on environmental engineering could last for decades. Their extraordinary oxidation potential, broad reactivity, and ability to destroy persistent pollutants make them one of the most important tools in modern wastewater or water treatment. And as a concern over emerging contaminant continues to rise, hydroxyl radicals will undoubtedly remain the center of future wastewater technologies. In our next video, we will explore one of the most widely used advanced oxidation process, the Fenton process, and understand why a simple combination of iron and hydrogen peroxide can become a powerful treatment technology. If you found this video useful, don't forget to like, share, and subscribe to Clean Copper Talks. Thanks for watching, and I will see you in next video. Till then, tata, bye bye, take care.